once you have a population of interest, and if we take, let's say, the first sample of size 4, and we can calculate the average based on that sample, which probably we could call x1 bar. And from the same population, we can also take another sample of size 4, and we could call that average as x bar 2. So note that x1 bar and x2 bar need not be exactly same. Although we are taking a sample from the same population, every time you take a new sample and calculate the average, those averages need not be same. They can vary. So the averages also will be random variable. If you repeat this process several times, as indicated here, now if your original distribution looked like this, the new distribution of x bars, so here the x-axis is actually x bar, and you can see that the new distribution of x bars will be narrower. So compared to the original distribution, which has so much of variation, this one will have lower variability. So basically, central limit theorem states that sampling distribution of x bar having sample sizes of n will have a mean same as the original distribution. So there is no change in the mean. The second point is it has a standard deviation, which is given by sigma of x bar, and it is sigma divided by square root of n. Because we are dividing it by square root of n, you can see that this variability will be less than the original distribution of x. The third point for central limit theorem is tend to be normal as the sample size becomes large. Now in statistics, anything more than 30 is considered large. So whatever may be the original distribution, the final distribution will look like normal distribution if the sample size is large enough.
In a nutshell, basically it says that under some conditions, every distribution tends to become a normal distribution. So we have covered normal distribution earlier, and I mentioned that it is one of the most important distributions in statistics. Let's say there is a variable x and it has some shape, maybe irregular shape. Another variable, maybe it has a rectangular shape. Another variable may be right skewed. Another variable may be bimodal. Whatever shape it might have, under some condition or the other, all these distributions tend to become a normal distribution. That condition under which they become normal distribution is very simple. If you take a sample size greater than or equal to 30, so in statistics, anything more than 30 is considered a large sample, and then create distribution of x bars. So please note that the x-axis I have put here is x bar and not x, which means if I take, let's say, a sample of size 30 from the first distribution and calculate x bar, I may get, I'm just making up some numbers, maybe 25.3. From the same distribution, if I again take a sample of 30, maybe I may get slightly different number because there's no guarantee that every time I will get exactly same average because the sample elements might change. So this way you can get different x bar values from the same distribution if we repeat the process. And from these x bar values, if you create a distribution, which I have created here, it will be a normal distribution. So the mean of this distribution will be equivalent to or close to the population mean. And standard deviation, now I am going to use sigma of x bar. So standard deviation when we are using x bars, this is sigma divided by square root of n. In this case, sigma of x bar is called standard error. Sigma of x is called standard deviation, but sigma of x bar is called standard error. So that's the key difference because x-axis is now x bar axis. If you look at this formula here for the standard error, what it says is n, or the sample size, is in the denominator. Now, because n is in the denominator, as sample size increases, your standard error will come down. Your sigma of x bar reduces. So sigma of x bar reduces means the distribution becomes narrower, and basically our estimates become more and more accurate.
So this sigma of x bar, so the name given to this is standard error. So sigma is standard deviation, as you know. So to differentiate sigma and sigma of x bar is called standard error. And sigma of x bar, you can see it has a lower variability. The spread is less simply because we are dividing sigma by square root of n. So as the sample size goes up, you'll see that this distribution becomes narrower and narrower. You can see as the sample size increases, the line is coming down, indicating that the standard error also reduces, which basically means the shape of normal distribution becomes narrower and narrower. Like if your distribution of x bars, suppose this is with n equals 2. So as you go from n equals 2 to, let's say, n equals 10, this distribution of x bars will be much narrower. It may look like this. And if you go further to, let's say, n equals 30, it will look much narrower. So this could be the distribution of x bars. This is the idea behind central limit theorem, that as you have bigger and bigger sample size, the variability for the normal distribution becomes smaller and smaller, and also the shape is going to be looking like a normal distribution. So to calculate sigma of x bar, or standard error, so we know the formula sigma divided by square root of n. So we just plug in the values. Sigma or standard deviation is 14. So if sigma is not available, we can use the estimate, which is standard deviation is 14 and square root of 49. So basically 14 divided by 7, which is 2. Let's look. The x-axis is not x, but it will be x bar. I will show you calculation for n equals 30, and same thing can be done for n equals 50, 100, and so on. When we calculate, let's say, x bar or a standard deviation, it is a single number and it is called as a point estimate. So if we move to the next slide, why do we need a confidence interval? Sample statistics such as mean, standard deviation, so actually mean is x bar, standard deviation and proportion are only estimates, or more specifically point estimates of the population parameters mu, sigma, and p. And since there is a variability in these estimates from sample to sample, we can quantify uncertainty using confidence intervals. So note that when we are taking a sample from the population, like the first slide we saw today, from the population, when you take a sample of size 4 first time and calculate average, you may get one value. If you take another sample from the same population of size 4, obviously you may not get exactly same average. Your numbers can change because your samples could change. So that's why we have a variability of x bar, and we can quantify uncertainty using confidence intervals. So confidence intervals provide with a range in which population parameters are likely to fall. Generally, confidence levels we use numbers like 90%, 95%, 99%. This is more easily understood by looking at this picture on the next slide. This line in the middle suppose that is the real value we are trying to capture, and it is the population mean. And from the population, we take the first sample and create an interval by doing some calculation. We are going to see in next few slides how to do that. So suppose we create an interval, and you can see the first one actually includes the population mean, the real value. Second one also includes. But there could be a sample, because our sample is simply a random sample, and just purely by chance we can get the values in the sample which are all actually on the lower side. And when we calculate the confidence interval, it does not include the real population mean. So that can happen, and if out of 100 times that happens 5 times, that means our confidence level is 95%. This symbol here is called alpha. 1 minus alpha basically represents confidence level, and alpha is the opposite of confidence, so we can call it as risk level, risk of not capturing the population mean. So out of 100 times, if we are able to capture the population mean 95% of the time, then confidence level is 95%, but the risk level is 5%. And there is always a risk, because we can never have 100% confidence, because we are dealing with sample, and sample is only a part of the entire population. So it is incomplete knowledge or incomplete information. So that's why our confidence level cannot be 100% all the time, because we are dealing with a sample. Confidence interval generally has this format. We'll have a point estimate value like X bar or standard deviation and so on. So this is one term, and then there is a plus minus term, and that term is called as margin of error. So any confidence interval will have these two parts. So one example is like if you want to estimate what percentage of voters will prefer, let's say, candidate A in the next election, and suppose the point estimate based on the data is 45%, and then generally newspapers or magazines also report 45% plus minus some margin of error like 2%, for example, because they know that it is based on a sample and there will be some error. It cannot be exactly 45. If somebody repeats the process, takes another sample, that number may be 46% or 44%. So they also report margin of error. Now, how to calculate margin of error? That again will vary from situation to situation. So this alpha, apart from risk level, it's also called as significance level. We are going to deal with 4 different situations. One situation is confidence interval for mean when sigma is known, which is on this slide, and we'll talk about it first. The second situation we are going to talk about it is when sigma is unknown. Third will be confidence interval. Actually, it will be interval for sigma itself. And the fourth situation we'll talk about is proportions. So sigma is the population standard deviation, and sometimes a company may be dealing with a kind of data collection almost on a daily basis, and they are doing it so often that they already have some idea about how much sigma to expect. So in those situations, we can say that population standard deviation is known, and the confidence interval for mean can be calculated using this formula. So X bar plus minus Z alpha by 2 sigma divided by square root of n. In this formula, this part is the point estimate, so single value estimate. So X bar is a single number. Z, as you know, refers to standard normal distribution, and then the third part, as you know, is the standard error. So you can see the formula which we just now wrote is given here. So let's look at this example on slide number 31. So based on what is given, n equals 45, sample size is 45, X bar is 1.45, sigma. When you are reading the problem, you will notice that it clearly says population standard deviation is so and so. So unless it says population standard deviation, it is not a sigma known case, because here it says population standard deviation. That's why we are treating this as sigma known. And sigma is 32 cents, 0.32. It says 1 minus alpha is 95%. So alpha is obviously 5% or 0.05. So alpha by 2 by default is in the formula of the confidence interval. The only thing which is not given directly is z alpha by 2. Now to find z alpha by 2, I'm going to make a picture here, so you can use the same format all the time. This is z. So z always has a standard deviation of 1 and mean of 0. Area in the middle is 1 minus alpha all the time, and in this case it is 0.95. So the remaining area in the tails obviously is alpha by 2, and it happens to be 0.025 on either side. And this value is called as z alpha by 2. So this is what we need before we can calculate confidence interval. Now you can see the area to the left of z alpha by 2 is 0.95 plus 0.025. Total area to the left of z alpha by 2 is 0.975. We can calculate this z alpha by 2 using the Excel function NORM SINV, for INV for inverse, 0.975. The answer we will get is 1.96. 95% confidence interval. So I'm writing CI for confidence interval using the formula is 1.45 plus minus z alpha by 2, which is 1.96, times sigma is 0.32, and square root of n is 45 here. So if we subtract 0.09 from 1.45, and if we add 0.09 to 1.45, we should get 1.54. Going to the next slide, you can see all these steps which I just showed you is given, and that leads to this 95% confidence interval. Sample size of 57 analysts gives an average of 52,746. Sigma is again given. Again, it says population standard deviation. Then, because of that, we are assuming sigma is given. It is 10,000. 1 minus alpha, 0.95 again. So z alpha by 2, as we had done in previous problem, for 95%, we calculated it was 1.96. So note that this company advertises to the world that the tensile strength is 93 kilograms. There is a customer complaint that it has been coming down. 23 samples were tested, and the average was found to be 92 grams. Population standard deviation clearly is available as 4.7, and we need 95% confidence interval. The question is, are the concerns from the customer valid? Has 93 really reduced? And the sample says actually we have 92. But please note that this is a sample of 23 which is giving 92. Now if somebody takes another sample, we do not know that what number we'll get. We might get maybe more than 93. We might get 94. Take another sample, we may get average as 91. So we cannot look only at the sample average and decide that because 92 is less than 93, we should say the customer complaint is valid. But if you use confidence interval formula, remember we are using average, we are using standard deviation, we are using sample size, and then we make a decision based on all these parameters, not just the sample mean. So now we have a 95% confidence interval for mean. And note that this confidence interval does include 93. So that means the process actually has not deviated from 93. And we know that no manufacturing process on earth can give all components exactly equal to 93. So strength cannot be exactly 93 in each and every item this company makes. And that's like nature. The variability always exists. Based on the variability, the value of X bar is going to lie between 90.1 and 93.9. And because it includes 93, we can say customer complaints are not valid. If actually the confidence interval, which is based on data, came in such a way that 93 is not included and the entire confidence interval is on the lower side, then we could have said that the customer complaints are valid. Could be in this situation there is a need to maybe educate or inform customer to not be surprised that all the pieces do not have tensile strength exactly same as 93, and they should be made aware that the variability is a part of any manufacturing process. So sometimes the value could be more than 93, sometimes it could be slightly less than 93. Now when sigma is not known, the formula we'll see on the next slide is given by X bar plus minus. Instead of standard normal variable, we use a t distribution. So we write t alpha by 2 comma n minus 1. So n is the sample size, and instead of sigma you can use sample standard deviation s divided by square root of n. And the change is from standard normal distribution we go to t distribution. Now this t distribution actually looks like a normal distribution. The only difference is that in t distribution area in the tail is slightly higher, or there is more area in the tail compared to normal distribution. So let's look at the next slide, which gives the formula which I just wrote. Now key thing to note and compare with the earlier problems we did for sigma known case. Here it says the summary statistics for sample data, and based on the sample mean is calculated and also standard deviation. So standard deviation now is calculated from the sample. Population standard deviation is not known. Sigma is not known. So sometimes people get confused that standard deviation equals 9528. So sigma is given. But remember, this is not sigma, this is S, or sample standard deviation. So this number is sample standard deviation. So this is basically a sigma not known case. You can use T, I, and V because we have the probability in the form of alpha and we need to find the T value. So inverse calculation. And the first number we should put is alpha, and second number we should put is n minus 1. So this is also indicated on the next slide, and the steps are given. So this is also given on the next slide. One more thing I would like to point out, like if you have, let's say, a confidence interval which is for 95% and a confidence interval for 90%. So the idea of confidence interval is to capture the population mean. Higher confidence level means higher interval or wider interval for the confidence interval. And smaller, like if you go from 95% to 90%, your confidence interval will be narrower because the chances of catching the real population mean is lower because the confidence is lower, 90%. So the chance of catching the population mean also is lower.